Okay. So hello, everyone. We
Okay.
got our new systemic modeling seminar by JoeRiggo Reyes, the climate change landscape from a data science perspective. So thanks, Joe. Floor is yours.
Okay. Thank you very much, Dr. Velos. Good morning, good evening, good afternoon to the rest of you. It's very nice to hear the work that you've been doing, and I think, yeah, this group is gonna meet together at synergistic points because I think, for example, um, the economics plus the social systems plus the Bayesian frameworks, they would all go together. Uh, and I think I'm gonna be asking some questions from you guys later. So if that's uh, I'm looking forward to interacting with you guys. So I'm Joe. You can call me Joe. I'm from the University of the Philippines. I'm a second year PhD student in the data science program in our campus, Diliman. Um, I'm currently in Manila, Quezon City. Prior to pursuing a PhD degree, uh, I was a biologist. I am a biologist. Still a biologist. But I worked in the Philippine Genome Center, so I was also a bioinformatician. So I did a lot of genome assembly and assisted some projects in crafting their workflows for the bioinformatics that they're not yet so familiar with, especially when it was just first introduced here in the Philippines. So we're kind of the first, one of the first to do genomics and bioinformatics here. And then later on, I got kind of uh, realized that I need to do something about the the climate because I have kids and I wanted to the the main selfish reason that I have is what do I tell them 20 years or 30 years from now? Should I tell them to just not have kids or is it okay for them to have kids? That's the first question that I kind of had in my head, and then some other events that pushed me into okay, it's finally time to pursue a PhD. So and here I am, and thanks to meeting Dr. Bellos in one of the conferences last year, I approached him and he's just very friendly and he agreed to co-supervise me in my PhD study. So without further ado, I'm presenting some of the readings that I have. It's not yet the research that I'm doing, but sort of the background on what I want to do later on in the program. So the title of my talk is Climate Change Landscape from the Data Science Perspective, and it's kind of as a landscape, it's broad. I and as it is, I don't think I will be diving too much into the depth of each of the topics, but I'd like to put them into the perspective of data science as well. So who among here recognize these photos or these pictures?
Mhm.
Does anyone recognize these screenshots? They're from a movie.
Oh.
No one?
There is this I don't remember the name of the movie, but it's about the kind of climate crisis, extinction or something like
Uh, yeah, so this is from the Day After Tomorrow. It's a
Oh, yeah.
yeah, yeah,
movie
yeah.
way back in 2004. Yeah, so it's this storyline about the uh, Atlantic currents that have collapsed, and then as a result, there was this three super storms that were occurring across the globe at the same time, and that caused really massive damage. Like New York was submerged in 100 feet high. storm surge, and then a few days later covered in snow. And then there's this hurricanes in Hollywood that was unheard of. And I'm showing you this because just a few days earlier, there's also this news about San Francisco getting its own first tornado warning. And kind of hit me. That's the day after tomorrow scenario. And then what I mentioned earlier about the pretext of the movie was that the Atlantic meridional current, the Atlantic current, is collapsing. And then there's this study also earlier this year that says there's kind of good evidence that it's really actually slowing down. So kind of, hey, that's kind of creepy. What's happening? And then just recently, also in the last month, we have this six storms that hit the Philippines, one after the other in 30 days, and several of them were kind of a sorry about this. Were kind of a Category 4 or Category 5 hurricanes. So there's, for example, this two storms striking the northern Philippines, one after the other, that are both um, Category 4 hurricanes. And if you look at this, this is the first time also that it was said in this report. It's the first time that these four hurricanes or four typhoons were recorded at the same time since 1951 for the Pacific Basin. So there's something going on, I think. And then there's another report that says just a few days earlier, that says climate change did supercharge the typhoon season in the Philippines, like and highlighting the six hurricanes that just hit in November and October. And it said that this was twice as likely to have happened than if there were no climate anthropogenic forcing that was there, and it increased the the maximum typhoon intensity by about 7 kilometers per hour, and we should be expecting this about every 15 to 12 years if we continue at a 2 degrees future warning. And it's not just here in the Philippines. It's actually also documented for the hurricanes that hit uh, the US in the past years, like the recent one, Helene and Milton, that really devastated Florida. And it says that these hurricanes would have been Category 4 and Category 5 if it were not for anthropogenic forcing or human-caused climate effects. And here in the Philippines, it says that it wouldn't have been as powerful if there were no human-induced climate effects. Now, if we look back into some further back in time and look at the storms that were recorded, this is a global count of storms. We kind of hey, just in the past slides, we're kind of saying that there's something fishy or something really scary going on about the weather. But if we take a look, it's kind of in from 1980s to 2020s, it's kind of not really changing a lot. And if we look at the uh, El Nino indexes in the Pacific Ocean, it's also not really changing a lot. And the number of storms and the ACE, the accumulated cyclone energy, how for the year, how strong the total strength of the storms have been for that year. We kind of can almost trace that there's uh, correspondence between, for example, here between 1990s in 1990 to 1990, this is 1995, and the early 1990s, the occurrence of El Niños, the red peaks, would correspond to this region here, and then this one here would be the 1997, 1998 El Nino, and so forth. So there's kind of a you can kind of explain uh, why this is happening, and it doesn't necessarily have to do with human climate forcing. And then there's also but if you look at further down in time, from 1870, you might notice that there's this more frequent shifts between El Nino and La Nina. So it's kind of oscillating more frequently than before. So that's one thing to say about that as well. But still, I can't draw any conclusions from that. And then I guess in the abstract, it's that the first sentence in the abstract that I sent is that last year made headlines as the hottest year on record, and it's kind of a big jump between the average of the last 1980s to 1980s to 2022 average. And then we look at the 2024 data, and it's kind of going down. And there's another report that says that the 2023 global warming spike here, when we said that, hey, heat waves all over last year by October, and then it's so far from the average for all of the rest of the years prior. It's actually driven by El Nino, the ENSO, and they were able to attribute this ENSO without needing to invoke anthropogenic forcing. So it's not really well, we can't really say that it's not really because of anthropogenic forcing, but as it is, the natural variability might be uh, just so large that we can't really say that it's uh, for sure that it's anthropogenically driven. So there's this kinds of things that on the one hand you observe these things happening, but on the other hand, the climate variability may be still so wide that we can't draw any strong conclusions from it if we take the data together. But of course, there's a lot of caveats in those data as well that we need to consider. But those things are we have to say those things in the at front. But regardless of those things that I just mentioned, we are on track to increasing temperatures over the next decade or so. Right now, 2024 is said to be the first year to breach 1.5 degrees Celsius. That's set in the uh, Paris Climate Accord. And it says that if we continue on this track, the 30-year average, so it's breaking this 1.5 barrier doesn't mean that we're there. It's just that we're transiently going there. Next year might be a bit lower or so. But what they're talking about, the 1.5-degree threshold, is the 30-year average for 30-year running average for 1.5. So if we continue on this track, we will be on a long-term high temperature uh, scenario by 2030. So we will be breaching 1.5 degrees in the Paris Climate Accord by 2020, by 2030, if we
Joe,
continue on this path.
can I
Yeah.
interrupt you for a second? Because
Yes,
maybe
of
not
course.
everyone is aware of the 1.5-degree increase problem
Right.
of the Paris. So just to give us this, yeah.
Yeah. So I will have a slide on that also later. Or before that slide, I could probably also say that the if you've heard of the conference of the parties lately, there's this CO COP29, COP28, and then there's this COP16 from in I think Colombia. That try to, the different countries talk to each other to set guidelines, to agree on things that they need to do to mitigate or to adapt to mitigate climate change
Mhm.
globally. And the Paris Accord was the or the that was the product of COP25. So that's kind of a 4 years ago that they said that based on the current scientific evidence, we have to limit our warming to below 2 degrees Celsius by 2100. And even better, we have to limit it by 1.5 degrees so that we don't have any detrimental long-term effects on the planet. So that's the case for the 1.5 degrees Celsius. I will have another slide on that as well in the next few minutes. But we have to the what the agreement of the different nations, the different countries together is that we have, based on scientific evidence, we have to. It's best for us if we can limit ourselves to 1.5 degrees. And right now, it seems that we're going to reach that sooner than we thought, and that's going to be a problem. So what's really happening? So that's kind of also the question that I asked myself, and one of also the reasons I took up the data science program and wanting to apply it to climate change. I want to have a grasp of what's really happening. So I'd like to present some history and background on the climatology aspect, so that we kind of understand better what's happening, and then some perspectives from the data science side in terms of uh, the things that we can do and contribute to climate science. I will show some slides that have example studies that use machine learning for climate change or climate related studies. But I will also focus. There's a lot of machine learning techniques, but I'd like to focus on neural nets, a bit, just a really little bit on graph machine learning, a little bit on Bayesian learning, and a little bit on chemical organization theory. So studying climate change is not new. It's actually been first proposed by Arrhenius and some of his contemporaries as far back as 1890s, that CO2 has an effect on warming, on air temperatures. So you can probably remember Arrhenius as the winner in Nobel Prize in Chemistry, and the famous Arrhenius equation for the kinetic constant, for the kinetic, the Arrhenius equation for, sorry, I forgot what this equation
Yeah.
is called, but
It's the kinetic
that
rate.
relates the kinetic rate, that relates the activation energy with the temperature, so that the kinetic rate is dependent on the temperature, essentially. So what he did was he took some data from some of his contemporaries and tried to calculate for different latitudes, different angles of the sun, what the effect of what at the time they called CO2 in the atmosphere as carbonic acid. So a carbonic acid or CO2 concentration of 1 would correspond to the levels at his time. So he did some calculations to show that at 0.67 here at the different latitudes, this would be the effect of the lowered carbon dioxide. At 1.5 times the current levels of his time, they would experience plus 3.1 to 3.6 or 3.8 degrees of warming to different latitudes. And the take home of this table of his was that the equatorial regions won't be as much affected as the higher latitudes. And surprisingly, it's kind of a still more or less holds today. What his findings are for the effects of carbon dioxide on warming of the different parts of the earth. So with that in regard, it's if we look at the climate system, it's really just about energy balance. Wherein we have the sun that uh, inputs heat or energy into the earth, and the earth has some properties that allows it to absorb heat from the sun, and it allows it some of that heat to be reflected from the earth, so that there's only a proportion of the incoming heat that is retained in the earth. And the atmosphere has this peculiar way of trapping uh, infrared heat, such that the infrared wavelengths of the energy from the sun don't easily escape through the atmosphere. And what Arrhenius and his contemporaries said was that it's primarily because of water vapor and carbon dioxide in the air. That's what Arrhenius was trying to show in this earlier work. And if we look at this from a simple as a simple model, it's really just a few things interacting, right? But if we take the Earth, it's not just flat land. It's actually a lot of interacting components. We have the ocean, we have the terrestrial landscape, we have the topography, how the mountains, the terrain, how the terrain changes in land, how the terrain changes under the sea, how the waves are, where the sea ice are, where the clouds form, and so on and so forth. And adding to that is adding to the complexity of the biogeo physical sphere that the Earth is. There's also this social, political, and economic aspect that influences also this biogeophysical-chemical component of the Earth system. And that's what makes it so complex. And here we just see here a simple model of the carbon cycle, wherein you have photosynthesis as a response from the energy of the sun. You have photosynthetic organisms producing uh, oxygen that also takes in carbon dioxide. And in overall, there would be CO2 in the atmosphere, there would be CO2 that is dissolved in the ocean, CO2 that is taken up by photosynthesis, CO2 that goes, or carbon that goes into fossil fuels by the death and decay of plants, and so on and so forth. And we have to balance all these processes together so that uh, we stay in the idealized scenario, or in that idealized situation wherein uh, Earth is habitable and everyone's comfortable in a way. And here also is another simple model for the water cycle. Those are just the carbon cycle, water cycle. Those are just two components of more complex models, and wherein you have your evaporation of water from the ocean that gets transported to land, then rain falls, and those gets absorbed by the soil, and then there's groundwater runoff, and the cycle goes on again. And if we look at the carbon dioxide levels over time, this, of course, we have some observations only from uh, maybe 1800s or 1900s. And what we can say here is that since we invented cars, essentially, there has been uh, a rapid, very exponential increase in the levels of carbon dioxide in the atmosphere relative to pre-industrial times. So this is the pre-industrial times, which is the uh, flat region of the curve. And here we just show the, if we just take the 1960s to 2010, it's also an increasing trend, although we see at a very more finer scale that it's also actually um, uh, oscillating or fluctuating. So taking all those together, how do physical models work? It's actually, well, when you look at the television and hear the weather forecast in your local news TVs, that's the product of what this does. So their models actually take in thousands of cells or cubes that each of them would run uh, all the differential equations from all the different components that we have and that we have talked about and not talked about in the previous slides, that are calculated through time and taking into account both the atmosphere and the ocean. So these are ocean atmosphere models, because the ocean affects the atmosphere and the atmosphere affects the ocean as well as the land component. So here you have at the atmosphere, you have variables such as wind, humidity, clouds, temperature, and aerosols, chemical species that you can find in the atmosphere. And what you have on the upper levels may not be the same as what you have for the lower levels, or the concentrations need not necessarily be the same. Compare that when you just look at it from the top, where it's 2D, and you don't have that kind of information, how those different things move together, such that there's the rising of the warm air. You won't be able to capture that, and the interaction of the warm air with the cold air in the upper levels of the atmosphere. Those are things that the processes that cause the formation of, say, precipitation or formation of clouds, or the driving of wind currents, or the trade winds, or other climatological processes that uh, we observe. So, for example, here in the surface, we measure surface temperature, sea surface temperature, uh, carbon dioxide fluxes, which is the diffusion of carbon dioxide from the ocean to the water, from the atmosphere to the ocean, and vice versa, and so forth. So even if this is so complex, the limitation here is that, for example, a case in point, temperature is easy to model because it's kind of a spread over. It's almost homogeneous, but not precipitation, because precipitations are due to clouds, and clouds are smaller than the grids. So if you kind of taken a look at the weather.com satellite weather forecast, where you have a map and you try to zoom in, you can see that those clouds, as you pass by in your area, they look like pixels, or pixel. They're very pixelated because the resolution of those models are not really high enough to really tell you precisely what area in your neighborhood would catch rain. It's just an average of a larger area in your neighborhood. And the highest resolution for so far is 3 by 3 kilometers, and it's a regional scale, not global model. So there's one of the limitations of these physical models. They're very expensive to compute, but still they cannot really pinpoint yet um, very precise predictions for one example is precipitation. There are ways to try to do that, but they incur additional cost and the computational cost, of course. and they are not always being done by different meteorological agencies. So some of the good ones do, but not everyone does that. So this is a physical model of the of this. So what an Earth system? So that's a physical model. There's also an Earth system model wherein there's the notice that the physical model only takes in non-living variables. Uh, the Earth system model takes in the living components like biogeochemistry. So this includes um, the activity on land by living organisms, and marine biogeochemistry, which includes the activity on the ocean by living organisms, like the production of dissolved organic nutrients, or the leaf cover or vegetation cover that produces oxygen and takes in carbon dioxide, so that it knows how to balance it knows where the carbon dioxide in those grids above would be taken in by regions on land or in the ocean. So an Earth system model takes all of these components together into a coupler that in turn produces the variables that we are interested in, like precipitation, temperature, sea surface temperature, the ground temperature, sea surface temperature, and other variables. Now, this Earth system model is still also and just on the living, as in general, a living component. We don't yet have the complexity of the human involvement. So there's this coupling again to human associated factors, and they have this um, methods called representative concentration pathway and shared socioeconomic pathways that try to force or try to model how the activities of humans would uh, affect the levels of CO2 uh, in the atmosphere uh, based on, say, in general, socioeconomic factors like um, the economic performance of countries, the population of the world, or education of different the demographics of the education of different countries and so forth. So those are factors that are being taken in by these RCPs and SSPs. And here, for example, in the shared socioeconomic pathways, here for the RCPs, we have these socioeconomic scenarios wherein you have your land use and cover data and your emissions data that are then put into, similar to the physical models, they're gridded all over the earth, such that when it produces an output, it's also you can also kind of overlap or overlay the outputs of these RCPs. These are the effects of humans on the physical models that are the products of the Earth system numerical simulations. Yes, hello. Okay. So these are some of the outputs of the RCPs, and these are for the socioeconomic pathways. So there are narratives or storylines. I think there's some of that on the next slide. There's these scenario drivers that can be quantified, like population, urbanization, and GDP. And for the outputs, we have these greenhouse emissions that are of interest, land use change, and air pollution, air result emissions that should be directly compatible with the physical models. So here we take the SSPs, and then we take the physical models, and what this outputs is based on the projections of the forcings. So forcing meaning those are the variables that you sort of the independent variables that you push towards this model, the Earth system model, such that it responds to to those forced variables. And what it outputs then would be something like this is one of the many outputs. It provides a lot of other metrics, but among them are temperature, of course, and global greenhouse gas emissions. So for here, for temperature, we have these different SSP scenarios wherein if there's lots of mitigation, we would have this temperature by 2100, and if we go business as usual, we would be reaching as high as this by 2100. So those SSPs and RCPs can be combined together into sort of five narratives. So for SSPs, we have narratives for sustainability, wherein we have rapid technological advancements and adoption of alternative energy modes, for example. Uh, we have rapid growth, a middle of the road scenario wherein, yeah, we kind of stick to the uh, prescriptions of the Paris Accord that we limit 1.5, but I can't really do all of that. So it's the middle of the road. And then there's a regional rivalry wherein this would be examples of these would be the conflicts, for example, or um, uh, individualism among nations, wherein, hey, I want to benefit more than you, something like that. And then there's inequality. This is in terms of the across nations and within nations. There would be poorer nations and there would be richer nations that have more or less access to climate mitigation and adaptation modes. And then there's here rapid growth when there's just unabated use of fossil fuels. We don't uh, try to uh, the economic performance is more important than the environment. So here in this axis, we have mitigation challenges in the y-axis and adaptation challenges on the x-axis. So mitigation meaning how do we bring down the levels of CO2 in the atmosphere, and on the x-axis, how do we adapt or how do we respond to extreme changes in in the future. So if, for example, here in inequality, although there would be low mitigation challenges, meaning there could probably adoption of new technologies for green energy. Not everyone is able to access that technology. So there's a lot of the other nations that are poorer would not be able to adapt to climate change, and as a result, it's not a very pleasant world for everyone. So this is the stories with SSPs and RCPs. Now, in essential climate variables, these are the sort of the markers for that we can keep track of. These are physical, or chemical or biological variables that contribute to the characterization of the Earth's climate, and we can measure them uh, globally, and they are cost effectively done. So currently there's 55 of them, and among them, for example, here, uh, precipitation, uh, sorry, this is precipitation, for example, and then there's sea surface temperature, ocean waves, there's biodiversity index, and so forth. So that's just the list of those essential climate variables. And why is it important to keep below 1.5 degrees? So there's this paper by Richardson and the group of Johann Rockstrom from the Potsdam Institute in Germany for climate change impact. Last year, they said that we have already gone past 6 of the 9 planetary boundaries. So these planetary boundaries here in the green circle This is what they said is the safe operating space for the Earth, such that if there were perturbations that would happen, there's still enough buffering that can absorb those perturbations without having to go into another state or into chaos or something like that. But with if we transgress those boundaries, we don't have enough cushion, we don't have enough uh, uh, buffering capacity to absorb um, perturbations or extreme events. And it's more likely that the Earth system would tip into a into another state that more likely than not would be less favorable than it is now. And right now, there's six of those that have been transgressed according to their metrics or measurements. And those are this is freshwater change, biosphere integrity in terms of genetic, because there are papers that have quantified lots of extinctions now in the different species on the surface of the earth, such that they warrant saying that we are experiencing another great mass extinction event now, currently. And
Sorry,
there
Joe,
are, yes,
can I just ask, so what is the difference between biosphere integrity and the functional? It says functional. What does that mean?
yes, so biosphere integrity in terms of so this is there's the this sorry this is functional and genetic. So these two are in terms of biosphere integrity. So
Mm-hmm.
there's genetic integrity and there's functional integrity. Genetic integrity means that the diversity in terms of the number of species are really declining. The
Mm-hmm.
functional integrity means that even if you have in an ecosystem, even if you have less number of species, those of the remaining species can still do the basic functions of the niche or the ecosystem, such that the ecosystem still doesn't get collapsed. So uh, you may have sort of the genetic diversity if it's high. It may not necessarily mean that removing a lot of species there would result in a functional collapse if there would be remaining species that it can still do. It's sort of a parallel or backup species that can still do the functions of those that have
All
gone
right,
away.
that's clear.
Yes.
Right, thanks.
What about novel entities? What is that?
Novel entities are those that have not yet been, I think, quantified or identified. So that's why this kind of vague instead of these ones that you can see are sharply defined. So it's kind of uh, an allowance for other um, boundaries or other elements that are relevant to the planetary boundaries that have not yet been clearly identified, if I remember that correctly.
Okay.
Okay. Yes. Okay. So here we have some of the uh, elements that have been identified as uh, tipping point elements in the ecosystem, in the global Earth system. And for example, here, the Greenland ice sheet and the West Antarctic ice sheet, well, what it says here is that the green line here is the 1.5 degree threshold. And what it says is that the Greenland ice sheet and the West Antarctic ice sheet are will be almost the first ones to collapse, or would be the first ones to have a tipping point once we cross or even maybe even before we cross the 1.5 degree threshold, if that stays on for so long. So those are the first ones that are likely to experience some tipping points, and then it would be a system of what do you call this? As a cascade of systemic failures, so to speak, because these ones are the first ones to collapse, and then the other ones would follow. But by themselves, these ones would collapse first, and then, for example, the Atlantic meridional oceanic circulation, the one that I talked about earlier. That's the circulation in the Atlantic Ocean that keeps the warm and cold waters in the Atlantic moving up and down to the depths of the ocean and then up again to the surface. That affects the weather patterns. It has a higher degree of certainty, but it might collapse in at 1.5 degrees. So those are things that we have to watch out for according to this to the group of rock structure. And these are just the same, I think the same figures for temperature projections with the different SSPs. And what they also mentioned is that there's this interaction among the Greenland ice sheet, the West Antarctic ice sheet, the Amazon rainforest, and the Atlantic meridional overturning current in the Atlantic. These are interacting together synergistically, and these are the most critical points that we have to watch out for, because once one of them collapses, the rest of the others would also collapse. So that's the take home of the this whole figure. And this panel here just shows, I'd like to highlight this first, and then this panel here just shows the amount of greenhouse gas emissions with different scenarios over time. And what you can notice here is that what I've been talking about is that we have to limit 1.5 degrees Celsius by 2100. But here we have the scale up to 2300. And what that means is that we have to limit if we have to overshoot by 1.5, we have to limit that overshoot and bring that back down more immediately. Otherwise, by 2300 or so, we would have catastrophic impacts because of the collapse of these different systems. And this is just the here the tipping scale in years of these four components. The meridional current is over hundreds of years. The ice sheets are over thousands of years, and the Amazon is over decades to centuries. So can we really distance ourselves? Yes.
So what is the certainty? So what is the probability of these graphs is now a single line, but I assume that they have kind of a spread of the probability of their outcomes. Can you say something about that?
Well, do you mean this bottom graph?
Yeah, well, these so it's like a tipping point, but presumably
Yes.
they are like projected kind of
Right.
areas in phase space where they might take on a different steady state, but that will not
Yes.
be
Well,
an exact point, but more like a gray area where things start to move irreversibly with a
yes.
probability. So how can I?
No, these figures don't actually show the probabilities. These figures just show here, for example, the temperature and the greenhouse gas levels by 2300. But what the study likes to point out is that identify the range of probable temperatures that these four would be at their tipping points. So here in this figure D would be the range of probability or the confidence or credible interval that the ice sheets, the meridional currents would be having at their tipping points with the bars as essentially a bar plot for the projected temperatures at which they would collapse.
Okay.
Yes.
Yeah.
But these first two line plots here are just projections of the temperatures.
Yeah. No, I was referring to the link between the two. So yeah, it's clear.
Okay. All right. So there are technological advances. We have more data and knowledge about how to go about. We have decreasing cost of alternative energy. But of course, as I said, the more complex challenge there, and what I was also excited to hear about what you're doing, is that there's this human component that involves political will, individualism, and conflicts that will affect all of these technological advances and efforts that we're trying to do. And there's this study by William Nordhaus, who's also a Nobel laureate on economics in 2018 or 2019. He tries to link economics with climate change. And what he drives at is economic growth leads to CO2 emissions, of course, because there's more industry, more cars, more energy demands, and so forth. And these rising CO2 emissions would force climate change, increases in temperature, erratic and extreme precipitation, sea level rise. And this would then, because of that, countries would have to adapt and mitigate these changes, climate changes. And of course, they would impose economic impacts and, of course, also ecological impacts because these natural events would also severely devastate, say, natural habitats if they are flooded, or if coral reefs would all die or bleach because of sea surface temperature rises and so forth. And what we need are climate change policies to reduce emissions, like carbon taxes, regulations that would circularize into more sustainable economic growth. So this is kind of a sustainable circle, and that it just boils down to having policies and rules in place that allow us to be sustainable. And he created this dynamic integrated model of climate in the economy, or the DICE model. It's similar to the SSPs and RCPs that try to project temperature and CO2 levels by a certain period. And here you have this the base, which is no mitigation or no climate, no business as usual. Paris extended is the if we continue on with if everybody agrees to the climate accord to keep within 1.5 degrees, but apparently doing that would also not lead us to 1.5 degrees or 2 degrees. It's gonna be overshooting to 3 degrees according to this model. If we limit the temperature to less than 2 degrees, then we may have a chance of achieving that to less than 2 degrees, but still we will be reaching 1.5 degrees according to this model. And the R4% and the R2% would be the sort of the rate of return if you did if you invested that much into the climate mitigation efforts. You would have rates of return of 4% or 2%. But as it seems, the discount rate at 4% would still lead to higher global temperature than if you were to have a 2% discount rate only. And this cost benefit optimal here, the CV optimal, places us at about 2.5. And what this tells is the figure here, wherein the climate accord says, okay, we have to do something now. We have to stop all our emissions now. We have to develop these green technologies and adopt them now, so that we would have this rapid decline, and we will be able to keep within 1.5 or 2 degrees of the targets. But economically, that's not feasible according to Nordhaus. And this is a more realistic scenario wherein we would have to deal with, assuming that we keep within the cost benefit optimal of this model, we would have to contend with living with the 2.5 degrees or more temperatures by 2500. So that's the take-home message of this slide.
But can I say something? I think
Yes.
above 1.5 or degrees, some of the changes that are set in motion will be irreversible. And because it's a complex system, they are likely to be unpredictable as well. And so any cost benefit analysis or kind of a net present value type of calculation includes a factor for risk. And at least the risk is unknown and it might be very high. So it's very, how can I say? This is a very arbitrary
Yes. Rejection.
calculation in that sense.
Yes.
Mhm.
Nordhaus has some critics as well. So, but yeah, for illustration purposes, it for me it makes sense that we have in this context that we need to change course now and just turn our backs right to 180 degrees. I think that's also not that feasible, and that has to be done within the economic and capabilities of each of the countries that would
Well,
be.
I,
Yeah.
sorry, you maybe there's no option. There's no other option than to do it. I think to take
Yes, there's no
make a
other
big
option than
change.
to do it.
Yeah,
Yeah, I agree, totally
and
agree.
and what sometimes I think might be a misunderstanding is that it's all seen as a cost, but all these investments in changes of systems, everything kind of needs to be changed from energy production to all value adding and industrial processes. That's all also invoices, and it's like people's incomes and salaries that are paid from that with an economic multiplier as well. And so it's not just only a cost, but also income for businesses and for people to make these changes. So I'm not sure if that's included in this calculation as well, but yeah.
Yeah, okay. I cannot quite answer you straight on that.
Mm,
I'd have to study further the paper by Nordhaus on
okay.
in terms of the risk in those kinds of calculations. Yes.
Oh, cool. Cool.
Okay. So we have some climate action that's going on. There's the UNFCCC, that's the Climate Conference of the Parties that I mentioned earlier for climate change, for biodiversity, and certification. So for climate change, what are the policies that we have to agree on? The most recent in the COP29, just this I think October or November, agreed that there has to be some funding for climate mitigation for the more disadvantaged countries. For biodiversity and the certification, I think the most recent COPs failed to get into agreements among each other for the nations that were there. So it's kind of a stalemate for biodiversity and the certification, at least for now. And there's sustainable development goals that aim to improve human lives while protecting the environment. And even if it's explicitly said here that SDG 13 is climate action, for me, it's actually all of these are for climate, because it's not just necessarily the physical component, but as you also mentioned earlier, it's not just cost, it's also income or benefit for the others, because if you have a healthy planet, then all of these will be possible as well. And to sum that up together, the climate change landscape actually consists of the biophysical taxon that has its own complex system, the social metabolic layer or taxon that has its own complex system. So these are the biophysical would be the natural Earth system. That's the Earth, the ones that we talked about earlier. Models of the social metabolic, meaning energy consumption, would be models of human environment interactions for social reproduction, maintenance, and growth. So essentially, that's energy input and output. It has its own complex system, and then there's this other complex system on the social cultural taxon that models the behavior interactions of human minds and uh, intangible uh, intangible qualities that inherent in human society. That's very difficult to model. And these three systems, complex systems, interact with each other and affect each other. And there's this term called the World Earth system that essentially is a human planet system that tries to encapsulate all of these. And from a data science perspective, so that's essentially the uh, the wrapping up what the climate landscape is about. And shifting through the data science perspective, we would be asking, okay, that's the landscape. So where are the data? So here in the slide, I'm just listing some. Of course, these are not all of the data in terms of the different complex systems that were identified in the previous slide. For example, the biophysical measurements. We have in situ reanalysis and remote sensing data. Remote reanalysis in situ data means we have sensors on the ocean, in tops of mountains, and so forth that are gathering and transmitting data. Remote sensing, we have your satellites like Google Maps. There are lots actually of satellites that are dedicated for Earth observation, for climate studies and Earth monitoring. And these include not just the visual that you can see in Google Maps or Google Earth, but also the different wavelengths of the electromagnetic spectrum, like infrared, ultraviolet, and so forth, that can further characterize things that we cannot see by just the red, green, and blue spectra. And then the reanalysis data would be data from products from models. Recall that in models, in situ data, we have spotty locations, right? We have one sensor in the Philippines, another one in Chile, another one in the Netherlands, and so forth. And then we build a model based on that. So the reanalysis data fills in the gaps in between those real points, so that we have a whole Earth coverage of data that we want in terms of, say, variables, essentially the essential climate variables like temperature, precipitation, and others. And these are usually housed in these websites or these repositories. So of course, a lot of them also be in literature that would not, that may not have already been incorporated into these central repositories. And then there's social metabolic statistics, for example, like the ones that were input for the SSPs or the RCPs, the GDPs, population, and urbanization. Those would possibly be obtained from organizations like the World Bank or IMF. Of course, if you go to each of the countries, you would have those data and literature, but of course, those are very difficult to do and obtain. And then there's those social cultural aspect. We have your SDG targets per nation. I know the Philippines has our SDG targets. We have your national pledges for the COP outputs, for example, for climate change. The nations would be obliged to, they're legally binding to be pledging, but not necessarily legally binding to do it. So that's the problem. So of course, there's per country legislation, policies, and government documents. Again, this would pose problems in obtaining and processing. There's news articles and social networks. Remember that the social cultural aspect does not just necessarily involve governments. These are individual behaviors and decisions also as well, and that encompasses, for example, those the decision makers in the government. So at the level of the individual, that's also important. And the challenges and opportunities with this data is that they're all time series, but they're not always aligned with each other. They're very heterogeneous. Some would be in table format, like biophysical measurements in Copernicus, but some others would be in text or in other media that you are not yet able to really model together as a coherent data set. There's inherent uncertainty, and there's certainty is unquantified in most of them, and there's mechanistic interactions that are unknown because of the uncertainties, and we don't know if they interact even, some of them. So in machine learning, we know that garbage in is garbage out. That's why it's very important to have very good data to start. And at least there are some efforts that, for example, climate change AI is. I signed up for this. It has a very active community. This organization I think recently launched this beta feature that details which data sets and what gaps are in those data sets for what sectors. So it's a community effort that hopefully they hope that can be built by both policymakers, end users, or climate modelers, scientists, and machine learning experts, and so forth. So this is still at the sort of infancy. So we still have a long way to go with regard to harmonizing all the data that we have for building a coherent social, cultural, socio-metabolic, and biophysical model of the climate system. So here it is, what I just said. And there's a paper that also surveyed the how machine learning can aid in climate change applications for climate change. So here we have climate change solution domains, meaning these ones, causal inference, computer vision, interpretable models, natural language processing, and so forth. And these are the areas where this can be applied. I know this is a kind of a busy slide, but I'd like to focus here on uniting data ML and climate science. Here, for example, we have for climate vision. I know this pertains to, say, for example, remote sensing and image classification for, say, the satellite data, for example, and say remote drone coverage or remote photos that could be taken in situ. And then interpretable models, very important. Time series analysis, of course, because climate data are time series, and uncertainty quantification. So on the other side of the slide, it's cross-cutting objectives, which include accelerated experimentation, control systems, predictive hybrid physical models, human interaction, and so forth. I will just, if you wish to go through this further, I will just point you to the reference in this paper. So I'd like now to move on to the specific interest points that I have in data science that might be of use in climate studies. And one of them is neural networks. So if we can review quickly neural networks, this is just a deep neural network. It just pertains to a neural network that has more than 3 hidden layers. So a neural network would have this input layer, multiple hidden layers, and output layer. It's called a universal function approximator. Just the 2024 Nobel Prize went to Geoffrey Hinton and the other winner for inventing essentially the techniques that use neural networks for the way that we use them now. And it's inspired by the neuron. That's why it's called the neural network, because neurons in our brain, they take in input from a lot of other neurons, and based on those inputs, it calculates in itself a threshold for it to fire. And then this axon is connected to the dendrites of another neuron downstream that contributes to that other neuron, and then that other neuron decides when to fire based on its inputs. And so this is the inspiration for constructing the neural network. It's also why it's very prevalent in saying it's for artificial intelligence. Essentially here, for example, in your input layer, you have this upstream neuron that connects to this other neuron that collects the input from all these other neurons, and then it decides whether it should fire or not, and at what intensity it fires. And then it propagates that signal to the other layers and so forth until you go on to your output layer, which essentially would be your predictions. And if we kind of backtrack again a bit, we could recall that the equation of the line is this, y equals mx plus b. And then if we have a multiple linear regression, it would be a multivariate feature. You would have several coefficients for each feature that contributes to this output variable. So this here you can explain which features contribute what to your computed value, plus a bias parameter. There's also this what we call a kernel trick, wherein you take a seemingly inseparable data set, apply your nonlinear transformations to your data so that they become linearly separable. And if we go back to this architecture of the neural network, if we take one node, that node actually looks like this, wherein we have your equation of the line, your weight, your input times the weight for that input and the bias term. Each line that connects nodes would have weights and biases, for example, and all these inputs would be summed to get a value here that is z, and then there comes a nonlinear transformation by a function on that value such that the output is based on that nonlinear transformation. And those nonlinear transformations is the activation function, and then it could be any of these two, or we could even invent more activation functions. And the way that neural networks are trained is that we have your training data, you propagate, you try to guess what the initial weights are, and then at the end compare your training data with the outputs of your model, and then try to readjust the weights for each such that your final predictions here match closely with your training data. And that is through a loss function for error minimization. And I think Geoffrey Hinton is the one who popularized or invented backpropagation. But I mentioned earlier that for multiple linear regression, we know exactly which feature contributes to what of the predicted value. But here, we kind of get lost on which weights and biases for which feature. That's why neural networks are deemed as black boxes, because yeah, it gives you very accurate predictions, but we don't know exactly what happened in the middle. We know there are weights. We can extract those weights and biases, but what exactly are those weights and biases representing? We don't know. So that's the thing. So there's ways of dealing with that, and say for example, computational ways such as sharp values, shapely values, to try to disentangle the contributions of your input features to your output predictions. But I'd like to focus on here physics-informed neural networks. which is adding constraints to loss functions based on model equations. And it's not necessarily explaining each of the nodes of the neural network, but rather by attaching a physical parameter or physical model to your neural network, you're at least assured that what your neural network produces is consistent with physical laws or a mathematical model. And it just adds physics laws to your data loss, as mentioned earlier. And it looks like this, wherein you have your typical neural network here that produces a value. And then that values then, or set of values, is input to your model equations. And then the results of those model equations are compared to your training data. And that loss is computed, and then the weights and biases are recomputed, and then the whole process starts over again. So at least at the end, what you get are physically consistent values that are predicted instead of just data consistent values that may not necessarily be physically feasible. And as a more tangible example of that is this Navier-Stokes physics-informed neural network, wherein you have your inputs X, Y, Z, and T. So these are the X, Y, Z coordinates in space and time. You would have these outputs, and then this would be the Navier-Stokes equations for X, Y, Z, and time. And then at the end, calculate them and readjust the calculate for the loss, and then readjust the weights and biases. So, what can we do, or how can we use these in climate studies? So maybe we can, physics-informed neural networks can be also used to replace or augment parameterizations in the physical models that we discussed a few slides back in the more complex Earth system models. Recall that there are, for example, clouds that cannot be seen by the models because they're too small for the grid. So those aspects, precipitation, for example, those aspects are parameterized instead. They're not explicitly modeled in the system. So what instead of having those parameterizations that can be hard to estimate and maybe erroneous or off at times, or we don't necessarily know the performance of those values or those parameters over different sets of interactions with the other parameters. A trained neural network can get its input from the neighboring cells and then output as a value the parameter that it's replacing. So that's one possible use. And then, of course, there's image classification for remote sensing data. There's the inverse problem for discovery of unknown phenomena. So if you don't yet know how component A and component B and component C interact together, but we know that they are there in the system, we can possibly try to model or discover equations that would represent those interactions. We don't necessarily know if those equations are true, but they can at least try to explain or have tangible representations for the observed relationships between those different variables or different components. And we actually tried this in a class that I had last semester. So here I took precipitation and surface, just two variables, precipitation and surface temperature, over this grid, very coarse grid over the Philippines, and try to model how surface temperature and precipitation rate relate to each other. So I took the reanalysis data from NOAA, and then made a time series of that, separated that into training, testing, and validation data sets, and then picked specific points for the testing or validation of the physics equations that will be used later or discovered later. So this is the data structure for that longitude and the latitude, the grid that was taken over time. So latitude 1 would have this time series, latitude 2 would have this time series, and so forth. And then it gave one of the iterations gave this kind of result, wherein the number of terms for I think this is precipitation, this is for temperature. 16 terms for temperature, 1 term for temperature. The XX means it's the second derivative of U. Of course, the exponents would mean the cube or the square. And different versions of that yielded these plots, wherein the blue lines are the true values and the orange lines are the predicted values. And so even if it's a very coarse data set, and there's only two components that are taken as input, given the complexity of the physical models that we have seen earlier in the first few slides, uh, I'm I would say that this falls quite near to the real values. Of course, not exactly the same. Of course, for precipitation, this is for precipitation rate, and this is for temperature. The temperature has obviously has some bias to it, but yeah, well, given that it's just taking two variables to try to model something that is usually done with supercomputers and lots of other data. Um, it falls quite near, but of course, uh, it's within. This is a limited study. I don't know how this would perform if it's a bigger area, or what would happen if I put the grids into smaller data, into smaller grids, or and so forth. But anyway, this is the project that I presented to the earlier class that I had last semester.
So,
And these are the
Joe,
yes.
I'm sorry to tell you, but I think we are a little bit past from the time of the meeting.
Oh yeah.
So I
Right.
want if we can wrap up with these results and we can have a little discussion after.
Yes, of course.
So because normally the talk is around like it's past like 20 minutes, 25 minutes. So I know everyone has
Oh,
to
I'm
go.
really sorry.
And we all want to have this little discussion, but tell us the end of this, and then the other methods we can maybe give a second talk for the specific
Okay.
more quantitative techniques.
Maybe I can just skip to the last part, if it's okay.
Yeah,
This is actually
that's all right. Mhm.
yep. Okay, so just I'll just skip this graph machine learning and the Bayesian approach and so forth, but I'd like to focus on here on the last few slides for what COT can apply, what COT can be applied to climate. Um, given that the reaction network, given that COT works in a set of reactions, um, and that it can do perturbation analysis, uh, I'm interested to see how that can be applied in this context, wherein you have obviously reaction networks occurring at the biophysical, sociometabolic, and sociocultural taxon, and how they interact with each other. And in the context of the planetary boundaries, wherein we know we have this organization at the boundaries, and then now we have this other organization that we're experiencing now. And then what are the other organizations that can be derived from these kinds of analysis perturbations? So there's also this aspect of COT wherein you have your calculation of your states based on the stoichiometries and the flux vectors, where in your flux vectors have your rate constants or kinetic rates. And there is also a chance for or an opportunity for uncertainty quantification of those, especially if, as I mentioned earlier, you don't know exactly how two things interact yet in the system. So I actually haven't compiled the list of references yet. I will send it. I will send the slide with a list of references. But thank you for your attention, and I apologize for going over time.
Well done.
No, thank you, Joe. It's
Thank you.
impressive work. I mean, sometimes it's you have too much to show. So obviously, we need more time. But actually, this is a first of many talks that you can give to the group, and I wanted to leave some time for a discussion of the principles of your research, because later on, I think many of us will be interested to go deeper in the particular models you are exploring, the Bayesian and the COT, and also the physics informed neural networks and so on. So, but like trying to keep it to the basics for now. As you guys, everyone probably know already, we have this project with Joe to make a collaboration between the VUB and the University of Philippine Diliman. We will run a couple of workshops. So the one at the VUB, it's going to be in February. I'm now confirming the venue. It's going to be most likely in the U Square, in the Brussels Institute of Advanced Studies, where all these like fancy new places are being developed, and hopefully in connection with the House of Sustainable Transitions, which is a little group at the VUB. Well, not so little actually; it's quite big group at the VUB with everyone involved in sustainability, lawyers, policymakers, engineers. So we're trying to build a very interesting interdisciplinary workshop. And I'm going to try to hook up to some people at the Copernicus as well, because Copernicus offices are in Brussels. So lots of things coming. I would like to open for questions. If anyone has a question or something urgent that wants to be said, maybe anyone here, I don't know, any questions?
Yeah, I'd like to throw something out. First of all, thank you. This was a very impressive, thorough discussion of modeling. It seems to me that there are three key, I mean, in other words, if we're not just saying what's going on here, but we're saying what's going on and what can we possibly do about it, then there are three key components to that. One is the modeling that you've talked about. A second one is incentives, and a third one is financing. And in fact, you can model those. In other words, you can say, what if such and such incentives were put in place? You started to talk about that a little bit with the example of the Nobel laureate. But I mean, there would be an incentive there if you say, from an economic point of view, you know, if we have such and such predicted extreme storms, these are going to be the costs, right? But then, so I think incentives can be modeling and then can be modeled, and financing is a really huge question. And you seem to be assuming that we're in the good old world where if the models are convincing, then the policy will be put in place by the governments to make all the right things happen. And we've seen that that's not happening. So there's got to be some, you know, I think financing, we're moving in a direction. First of all, the empire of the US is falling apart. So, you know, the US dollar is not going to be the kind of, you know, there are going to be other types of constellations, consortia of nations, and perhaps just big money coming together to address some of these things. There's even a cost of some talk of some kind of global tax on the ultra wealthy. so that the ultra wealthy globally are helping to pay for some of these things. Anyway, I think not just getting totally lost in the modeling of what might happen, but saying, you know, what can we do about it and how might we do it economically would add a lot. That's it.
Yes, I totally agree. But I guess also shown earlier the steep drop. It has to be those what we need to do has to be realistic as well, I guess. Yeah. Within the time frames and the resources that we have. But we have to do it as Dirk
Well,
said.
the interactions
There's
are
no choice but
so
to do it.
complex, right? As you show, that you know,
Yeah.
the change in ocean surface temperature and the loss of biodiversity, and so the interactions are terribly complex. I think when you at the end, when you started to look at your Philippine model, the question is: are there ways to start looking at regional models that can at least, you know, be a starting point to make a difference region by region, and then can you put in place Mark Jacobson at Stanford, I think he had a very limited idea, right? Very limited idea of looking at governmental jurisdictions that could put in place alternative energy requirements, and then analyzing just for those jurisdictions what would be the financial implication within that jurisdiction. So he would couple his work with, you know, and typically he was funded by the jurisdiction to do it, right? That was a very limited idea, and probably not that effective, but it is an idea of coupling the analysis to an implementation strategy. And maybe Dirk, here, that fits in your domain, you might have ideas on that.
Yeah, should you be okay? So no, I have no real comment. I just have a recommendation because I believe that regional strategies have a limited impact because it's a global complex system. So I can recommend one or more articles by Martin Scheffer. I put it in the chat, which is called, I think it's a research program which is called Governed Earth, by which it's philosophical, theoretical, thinks about how we can, as kind of astronauts, govern the Earth to a safe future. And the background of Professor Scheffer is in resilience of complex systems. So he looks a lot at the resilience towards these particular tipping points. So that might be interesting to you. Joe.
Thank you.
Welcome. Yeah.
Yeah. Okay. So I will stop the recording now. Tuck.